Hey everybody, and welcome to yet another lecture in finite math. Today we're going to talk about methods of counting. So far, counting has not been a real problem for us. Doing probability exercises, we have to count the number of outcomes that yield the event that we want. And we have to count the number of outcomes total. And so far, that hasn't been a real problem. For example, if we toss a coin and we follow that up by tossing a single die, we can actually write down all of the different outcomes and count them. Let's see, we can get heads and we can get a 1. We can get heads and we can get a 2. We can get heads and we can get a 3. We can get heads and we can get a 4. We can get heads. Did I do this right? We can get heads and we can get a 1. We can get heads and we can get a 2. We can get heads and we can get a 3. We can get heads and we can get 4. We can get heads and we can get 5. We can get heads and we can get 6. Okay, those are all the ways that we can get heads. We can get tails and get a 1, tails and get a 2, tails and get a 3, tails and get a 4, tails and get a 5, tails and get a 6. That's 12 different ways. If we do something like tossing a coin and follow it up by tossing a single die, we can count the outcomes easily. We can do the same thing even if we toss a single die and then take another die and toss it. We can count the outcomes. We can write them out explicitly and count the number of outcomes. In the case where we toss a single die twice, or where we toss 2 distinct dice once, there are 36 outcomes. We can actually write these down. Some situations, though, are such that there are so many outcomes that we can't possibly account for them all and count them all without some special tools in mathematics. Here's the first special tool, the fundamental counting principle. And we're going to do this in the context of a 2-stage experiment. Given a 2-stage experiment in which the first stage has n sub 1 distinct outcomes, and the second stage has n sub 2 distinct outcomes, the experiment has n sub 1 times n sub 2 distinct outcomes. So if the first stage has n sub 1 distinct outcomes, and the second stage has n sub 2 distinct outcomes, the experiment has n sub 1 times n sub 2 outcomes. And if we think about the experiment where we toss a single coin, and then we follow it up by tossing a single die, remember there were 12 distinct outcomes. Tossing the coin, there were 2 outcomes, either heads or tails. And tossing the die, there were 6 outcomes. Total number of outcomes was 12. And about 2 minutes ago, we just counted the total number of outcomes, and there were 12. So this formula works. Let's try some examples. Here's a good exercise. Oh, we're doing a deck of cards again. A single card is drawn from a deck. Its value is observed, and the card card is returned to the deck. The deck is reshuffled. A single card is drawn from the deck and observed. The first event here, or the first stage, is that we select a single card from the deck. The second stage, we select another card from the deck. How many different outcomes does the first stage have? We select one card from a deck. How many different outcomes are possible? We select one card from a deck of 52 cards. N sub 1 equals 52. The first stage has 52 outcomes. Well, this first card we returned to the deck. So the deck still has all 52 cards. The deck is reshuffled so that every card in the deck is equally likely to be the one that we select in the second stage. So in the second stage, the number of outcomes is still 52. So this two-stage experiment has N1 times N2 outcomes. 52 times 52, and oh my goodness, what is that? I think 2,704 outcomes. I think I'm right. We have a two-stage experiment. We draw a single card from the deck and observe it. That's the first stage. We put the card back in the deck and reshuffle it. We select another card from the deck. That's the second stage. The number of outcomes of the first stage is N1 equal 52. The number of outcomes of the second stage, N sub 2 equal 52. The experiment has N1 times N2 outcomes. 52 times 52, which equals 2,704 outcomes. Now, you know we're not going to leave this exercise alone. We're going to throw a slight twist in it. This exercise involved drawing two cards from a deck with replacement. So what do you think we're going to do next? We're going to draw two cards from the deck without replacement. That's right. We repeat the previous experiment, but we don't return the card to the deck when we draw the first card. A single card is drawn from a deck. We observe its value, but the card is not returned to the deck. This is the first stage. Did I squeeze all of that in? I guess I did. First stage. After we select that card, we reshuffle the deck, and a second card is drawn from the deck and observed. This is second stage. Now, when we performed the first stage, there were 52 cards in the deck, and we selected one of them. The number of outcomes of the first stage is 52. In the second stage, there were only 51 cards in the deck, so the number of outcomes of the second stage, yikes, is 51. The number of outcomes of this two-stage experiment is N1 times N2. 52 times 51. Oh my goodness, I think this is 2,652. I hope that's what it is. It's 51, I'm sorry, N1 times N2, 52 times 51, 2,652 outcomes. This is a nice example, and it doesn't involve coins, it doesn't involve a deck of cards, it doesn't involve dice. A two-year community college has 421 freshmen and 376 seniors. One freshman and one senior are selected at random to represent the student body at meetings of the Board of Trustees. How many distinct pairs of student representatives can be selected in this manner? One freshman is selected That's the first stage. This is a two-stage experiment. First stage, select a freshman. Second stage, select a senior. So selecting a freshman is the first stage, and selecting a senior is the second stage. How many different outcomes does the first stage have? There are 421 freshmen, right? N1, 421. The second stage, how many distinct outcomes? There are 376 seniors, and each one of them would be a distinct outcome. This is a two-stage experiment. Select a freshman, select there are N1 times N2, and that's 421 times 376. Holy moly, I worked this one out in advance. 158,296. Possible pairs. Son of a gun, that was a good exercise. But we'll have to use this in modified form somehow. We'll build on the foundation that we've just laid. So far, we've been talking about two-stage experiments. We're going to generalize that now for all multi-stage experiments. And here's the general counting principle. Given a multi-stage experiment in which there are k stages, suppose that the first stage has n sub 1 distinct outcomes, the second stage has n sub 2 distinct outcomes, the third stage has n sub 3 distinct outcomes, dot, dot, dot. The kth stage has n sub k distinct outcomes. Then this k-stage experiment has n sub 1 times n sub 2 times n sub 3 times dot, dot, dot times n sub k distinct outcomes. In other words, the number of distinct outcomes of this experiment are the number of distinct outcomes of the first stage times the number of distinct outcomes of the second stage times the number of distinct outcomes of the third stage, dot, 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 times the number of distinct outcomes of the kth stage. And I think we can refashion one of our recent examples to illustrate this. This is similar to what we did before, but now this is a small private four-year college. It has 189 freshmen, 181 sophomores, 176 juniors, 183 seniors, and one freshman, one sophomore, one junior, and one senior are to be randomly selected to serve on a four-member team that will represent the student body at meetings of the Board of Trustees. How many distinct four-member teams are possible? How are we going to do this? If you're thinking that this is a four-stage experiment, you're absolutely right. The first stage, a freshman is selected. The second stage, a sophomore is selected. The third stage, a junior is selected. The fourth stage, a senior is selected. How many different ways can we select a freshman? 189. So N1 is 189. Stage 2, how many different ways can we select a sophomore? There are 181 sophomores. So N2 equals 181. Stage 3, a junior is selected. There are 176 juniors. N3, 176. Stage stage 4, a senior is selected. There are 183 seniors, so n sub 4 is 183. Okay? And I'm going to get myself some board space. Excuse me for a second. How many distinct teams are possible? According to the counting principle, n1 times n2 times n3 times n4, 189, 181 times 176 times 183. Holy moly. This is the number of distinct 4-member teams. 1,101,803,472. Thank goodness it was a small private 4-year school. Oh my goodness. And you know something? An example like this shows why we value the generalized counting principle and the fundamental counting principle. There's no way in the world that we could list all of these distinct outcomes. We can't just write down all the distinct outcomes and count them. First of all, there really wouldn't be enough hours in a lifetime to do that. Second of all, if we had to write out all of these outcomes, we'd make a lot of mistakes in the process, and in the end, what we got probably wouldn't be very close to the true amount. So these counting principles help us to count the number of ways things can happen. And they're especially useful when it's impractical or impossible to write out all the distinct outcomes. Now it's time for us to look at another counting tool. And this tool is Factorials. Let n be a positive whole number. Then n factorial, denoted by n with an exclamation mark after it, is defined this way. N factorial equals n times n plus 1, n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. In other words, n factorial is n times every positive whole number less than itself. So let's see how this works. 1 factorial. What do we get if we multiply 1 by every whole number less than itself? We just get 1. Okay, what about 2 factorial? Maybe this will be a little bit more interesting. 2 factorial is 2 times every positive whole number less than itself. So that would be 2 times 1, which equals 2. 2 factorial equals 2. What about 3 factorial? 3 factorial is 3 times every positive whole number less than itself. 3 times 2 times 1. 3 factorial is 6. And 4 factorial? Well, you guessed it. This is going to be 4 times every positive whole number less than itself. So that will be 4 times 3 times 2 times 1. And that's going to be 24. 5 factorial is going to be 5 times 4 times 3 times 2 times 1. And that's going to be 120. And so on. By the way, your calculator should have a factorial button on it. Your calculators, the one that you'll be allowed to use in the final exam, they should have a factorial button on it. And it will probably have this symbol, and with an exclamation mark after